And now we're in the second of two videos on using color in computer graphics. We ended up with a meter that I use to measure LAB coordinates. And that's useful in some kinds of hard copy. It's also useful in some kinds of color 3D printing. Things like that, especially when you're trying to do something on a graphic screen and make sure that when you print the hard copy or do the color 3D printing, that the color is a pretty good match to what you saw on the graphic screen. But now let's talk about some rules of thumb. And one of the rules of thumb that I find really useful is a good contrast. And a lot of people think that if you use two colors, a background of dark blue and text of black, well, it's two colors, therefore you should be able to read it. And that's not it. It's really the change in luminance that makes the difference, okay? Which is loosely equivalent to contrast. This is not terribly readable. Color alone doesn't cut it. This is much better. It's a much better contrast. So two colors is not what you really care about. It's contrast that you care about. And this matters if you're printing a poster or you're doing PowerPoint slides or anything. You want things to be readable. Well, how can you figure this out? You know, and people get this wrong all the time. This is an invitation I got to something at OSU. I have no idea what it was. That blue and the purple just, there's no contrast there. Anyway, here's how you know. In the 1930s, when people were doing research on color television, and they couldn't do color television in the 1930s, the electronics wasn't fast enough, but they knew it would come eventually. And so they did a lot of experiments with human vision. And what they found out is that our perception of luminance, our perception of brightness came 30% from red, 59% from green, and 11% from blue. And well, luminance is abbreviated Y. I could joke and say, oh yeah, it begins with Y, but the Y is silent. No, I think it goes back to a luminance in a different language. But anyway, and this matches what we saw in those color scales before, is we are much more sensitive to green, less so to red, and horribly to blue. So if I have a certain color, I can compute its luminance. I can take its RGB, plug it into this, and get its luminance. So for instance, well, black is 000, that's a luminance of 0. That's not very interesting. Red, well, red is 100 times zero point 0.3 is zero point 0.3. Now it's more interesting though if we combine them. So cyan is blue and green. This plus this is zero point 0.7. So cyan is pretty high luminance. Yellow has a great luminance, second only to white. And my general rule of thumb, and I'm not sure there's any science behind this or much science behind it, but I know from experience that if I can get a delta luminance of about zero point 0.4 or better, then that's not bad. Okay, so for instance, blue text on a black background. That delta luminance is 0.11. No, that is not readable. However, you know, white background with blue is 0.89, or works the other way too. Blue background with white text, that works too. And so the colors that have been yellowed here are pretty good combinations. Delta luminance, the ones not yellowed, no, stay away from those. So this is how you can tell. Yeah, you can make little diagrams like this. So yes, um, you know, blue on black, not so great. Oops. Okay. It turns out we as humans are not good at discerning lots of colors. Okay. So supposing I put up a display and you're supposed to press red to log off normally, plus press light red to delete all your files. Okay. And I give you this. Are you sure you can get it right? We are just not that good at absolute color perception. So don't do that. Limit the number of colors. You've probably seen scientific displays where they've got 30 different colors in the color scale, and you can't match that. We are just not good at absolute color perception. Okay. Um, the ability to discriminate colors changes with the surrounding color. This is called the simultaneous contrast illusion. You've seen this before, I'm sure. This bar is all one solid color. However, with a green background, this looks lighter than that, but it's the same color, as you can see here. Now, here it's even worse. Here, if it's one solid bar, well, you can kind of get the sense it is one solid color, the same color. But here, yeah, wow, that looks like two different colors, although clearly it's not. It's even worse than that. Okay, so here's three solid horizontal bars of red, green, and blue. Each bar is the same color throughout. Let's change the background. Okay, look how different the red over here looks from the red over there. Same with the greens and the blues. And what program lets us change to a shaded background so easily? PowerPoint. So if you're displaying data, if you're using color to display data in a PowerPoint presentation, do not use a shaded background. It will screw up human perception of what those colors actually are. Here's an interesting example too. I contend that these two squares are identically shaded. They don't look like it, do they? Let's just move that one over here. And it is. Want to see it again? What's happening is it's a shaded or shaded square. It's darker gray on this side and lighter gray on that side. Darker gray on this side, lighter gray on that side, but you're focusing on that. And you're saying difference, difference, difference. And you're not focusing on the whole square. So yes, let's do this one more time. Click. Yes, it is identical. Here's another example, and this is sort of like the PowerPoint with a shaded background example. Over on the right side are 20 colored squares. This square matches one of them. Can you tell which one? It's very hard to tell because the person who did this display, this data visualization display, used the PowerPoint shaded background because it's cool. Well, it turns out the answer is this one. And if we were to move them closer together, this way, I think this one looks much brighter because it's got the black surrounding it. Now, if we move it over there, yes, you can see that indeed the colors match up. Oh yeah, no discussion like this would be complete without a damn blue dress. Well, okay, so here's what's going on, and we can talk about this more in class sometime. There's something called color constancy, and color constancy basically means there's a certain amount of compensation that goes on in your brain based on what you think the color is. So for instance, if I took a piece of white Xerox paper, photocopy paper, and I showed it to you in a conference room that had incandescent lights. Incandescent lights are slightly yellow. And I showed you that piece of paper and I said, what color is this? You would say white. Well, why would you say white? Because you know it's white. And so you would sort of ignore the environment color around it, the ambient color, and you would say, yeah, it's white because I know it's white. Well, that's what's going on with the blue dress. Is it really depends on what you think this person is what environment you think this person is wearing the blue dress in. Okay, so if you think that the person is in a shadow, then you know this must be the real color, because in a shadow, well, that looks like this. But if you think they're in bright sunlight, then you think it's this because, well, the bright sunlight part matches that. And that's what went on. Is some people thought that this person was in a shadow, and some thought that she was in bright sunlight. And so their eye-brain combination started compensating for the light environment around the dress. And so that's why some people thought it must be yellow and some people thought it must be blue. And the internet exploded over something that is sort of trivial. But anyway, that's called color constancy. And I always use the white piece of photocopy paper is my favorite example, but boy, I'm sure going to use the blue dress now because that's one everyone has heard of. All right, after images, everybody stare at the black plus sign. Now, and if you want, you could pause the video and stare at it even longer, but this should be enough. So if you stare at the black plus sign, so what's going on? Remember when we talked about rods and cones, you have cones in the back of your eye, and they are loosely red, green, and blue. So like anything in your body, it's possible to fatigue it. So you can fatigue the cones. So that red square, keep staring at the plus sign, but the red square is now fatiguing a square section of cones in the back of your eye. The green square is fatiguing a set of green cones in the back of your eye. Tick, 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 tick. And if we suddenly change it to an equal color stimulus, i.e. white, you see the after images because some of the cones are fatigued and the cones of other colors are not, and so you're seeing those other colors more strongly. I did a lot of my grad school work in a lab where there was the big computer graphics display was all green. The manufacturer billed it as a colored graphics display. Well, okay, green's a color. Yep, you're right. But it was weird because after using that for an hour, I'd stand up and lo and behold, the whole white lab around me looked pink. And it was this effect. So this will alter your perception of color. Here's another cool one. Does it look like these are scalloped, like the columns of a Greek temple? Yes, it does look that way, but they're not. They are solid bars of color. What's going on? Well, this is something called mock banding, and it works like this. Your eye is actually not able to take discontinuities in color. That is, here's what the intensity of the bars is doing, but since your eye cannot take rapid changes in color, your eye is overshooting and coming back, overshooting and coming back, overshooting and coming back. And so this is the scalloped look that you're seeing. This is known as mock banding. There's not a whole lot you can do about it other than know that it's there and know that you're not going insane when you see a certain effect like scalloped columns in something that you know darn well you drew as constant intensity. But it's worse. It's actually even worse than that. So here's a computer graphics display of, it's a heart data set I had once. And here all the polygons are drawn in their own color, which looks horrible, and we would never really do that. But if I turn on OpenGL Smooth Shading, which we'll talk about, um, do you see a white line right here and a white line right there? Those white lines don't exist. If I took a color meter and held it up there, we wouldn't see them. They wouldn't register. And I know they're not there. I drew this. I know they're not there. So what's going on is not only can we not handle steps in color intensity, we also can't handle differences in slope, first derivative distance differences in color intensity. So here we have what's really going on in the diagram on the right, but we do that because we can't handle that discontinuity. Yeah, this drives you nuts. You know it's there. You can make it a little less obvious by using smaller polygons. These are pretty big polygons. by using smaller polygons. But mostly we just have to know it's there again so we don't go insane wondering how to get rid of that white line. In some ways, this is how I think about it. It's sort of like trying to round second base at a 90-degree angle. You can't do it. You overshoot. So you have some amount of, I suppose, visual color inertia as you look across that display. Okay, one thing to be aware of is color vision deficiencies. Typically, scientists don't call this color blindness. There's almost no such thing as color blindness, like can't see color. But color vision deficiencies are like what we normally would call red-green color blindness. And it turns out that about 10% of the Caucasian male population has one of these deficiencies. And that's a lot of people. So and it turns out one of my current grad students has it. I've had previous grad students who have had it. It's kind of weird when you're in computer graphics and you have this. But anyway, it's something to be aware of. So if you do some display in reds and greens, somebody with red-green color deficiency is going to see it all as the same color. And so, yeah, they're not going to get anything out of that. Some of these websites that we've talked about, like Color Brewer, will actually give you some color scales to use that will not get messed up by red-green color deficiency. So anyway, it is something to be aware of because a significant number of people are that way. Now, of course, why are more men than women? It's because that deficiency, that defect is carried on the X chromosome. I found these pictures of chromosomes. Gosh, they're pretty different. The Y, the male chromosome, is really dumpy. Like that's the couch potato chromosome, apparently. But anyway, males are XY, and so if you have this deficiency on the X chromosome, there's no way to fix it. Women are XX, and so if one X has the deficiency, the other X is there to fix it. And so that's why typically women don't have this kind of effect. What we do, of course, though, is we code information redundantly, and that's like on web browsers. The hyperlinks are a different color, but they're also underlined. So yeah, you code information redundantly. Yeah, different fonts, different symbols, different patterns. Here's a trick that map makers have known about this for years. If you've got two colors right next to each other, you can make that boundary look really crisp by putting a black line or a white line between them. And the reason is your cones are there for color and there aren't many of them. However, your rods are there for intensity changes and there's a lot of them. And so if you can create this artificial intensity change across there, then your rods get involved and you have a lot more of them. They're much more higher resolution than your cones. But map makers have known this for years, but it's a good thing for computer graphics displays as well. Because we don't see blue very well, don't put fast moving or high detail items on your display in blue. And really, if you can help it, put it on in a grayscale or white preferably, or green. Red, not so good. Blue, even worse. I once used a graphics display where the cursor was in blue and I couldn't find it. I would look at the screen and I simply did not see the cursor, even though it was right there. We are just not good at seeing fine detail in blue. Yeah, there we go. Yep, we're bad. Don't use saturated reds and blues together. Although this one's kind of fun. It goes beyond contrast. Yes, reds and blues may not have a good contrast, but as you look at this display with the red text on the blue background, does it look like it's kind of vibrating? Well, what's going on is reds and blues are at opposite ends of the color spectrum. And so your eye is attempting to focus on both and it can't because they're on opposite ends of the color spectrum. And so your eye is essentially going in and out of focus as it tries to focus on the background, focus on the foreground, focus on the background, focus on the foreground. You actually see this sometimes in rock concerts. They'll bathe the curtain behind the band in blue, they'll bathe the band in red, and it kind of looks like everything's vibrating. Yeah, sometimes people do this on purpose. Don't do it in your own graphics displays unless you're just playing around, which is kind of fun. Whoop. All right, other stuff. All right, these are some of my favorite optical illusions. Again, our vision is not really as good as we think it is. It is so easy to fool our vision. All right, here's a cool one. All right, count the white dots and count the black dots. What do you get? Well, okay. If you're looking at a dot, it's white. If you look away from it, it's black. This looks like a very bad bathroom tiling job, but I contend, well, you're forced to believe me, all of those lines are horizontal, and they just don't look it. I saw a building once. I was on a college campus, and it had tiles on the side, and it looked awful. But as I got up close to it and kind of followed the lines across it, clearly the lines were parallel. And the lines are parallel here, as you can see. But this building looked just terrible. But it was this illusion. Yeah, this is swimming. These little almond shapes are just sort of swimming there. Clearly it's a static image, but it looks like things are swimming. Same thing here. Whatever circle you look at stops moving. Whatever circles you're not looking right at are moving or seem to be moving. They're not really moving. I just love this stuff. Yeah, same thing here. Motion where there really isn't motion. And this is my favorite. This is wonderful. So there are two squares, one labeled A, one labeled B, and I think they are the same color. And if I hadn't told you that we're going to look at optical illusions, you might even bet money that they are different colors because boy, by gosh, they look different. Okay, let's run an experiment. So I'm going to isolate just those squares. Here we go, here we go. Uh-oh. Yes, they really are the same color. Let's look at a different way of looking at it. Again, I'm going to isolate them. Yep, B's are equal, and the A's is equal as well. All right, play that back and forth. It'll still drive you crazy. And there's some references here if you care. And at the very end of the class, I'm going to give you a much better list of overall computer graphics references. So all of these are in that as well. So anyway, knowing something about color, and especially knowing about some of the limitations of human color, is really, really useful in computer graphics. So I hope you've enjoyed that and use it well.